Okay, a square root function contains the square root of a variable. See, not very complicated. They're what's known as a radical function. And not radical in the 1980s, it's cool sort of way, but radical meaning this is called a radical. Okay. The expression underneath the radical is the radicand, and I'm not going to test you on this or anything, but just that way if you see the word radicand, you know what I'm talking about. Radical functions, or square root functions, the parent function is just y equals the square root of x. Okay, that's the parent function, that's the base. The type of graph is a curve. The domain, x has to be greater than or equal to 0 because we can't have negative numbers under our radical, right? We can't take the square root of -4. And then the range, we're going to say y is greater than or equal to 0. This is the base. And what we get is the square root of 0 is 0. The square root of 1 is 1. I'm not going to bother with the square root of 2 or the square root of 3. The square root of 4 is 2. 5, 6, 7, and 8, I'm not going to bother with. The square root of 9 is 3. So I'm only doing the perfect squares. And you get a curve. Alright, so if we graph 2 times the square root of x, and then we state the domain and range, okay, the first thing we want to do is we're going to make a table. Now, I can pick 0 because the square root of 0 is 0, 2 times 0 is 0, and I can pick 1, square root of 1 is 1 times 2 is 2. Am I going to pick 2? No, because it's not a perfect square. You only want to pick perfect squares.
How is 1 a perfect square? What about 0 though?
0 times 0 is 0.
I didn't think that could be.
Yeah, 0 is a perfect square. So I'm going to pick 4. Square root of 4 is 2 times 2 gives me 4. And then I'll pick 9 because that's the next perfect square. Square root of 9 is 3 times 2 is 6. Okay, and you'll also notice I didn't pick any negative x's because I can't take a negative square root. At least not yet. Not in the real number system. So if I start graphing these, I have 0, 0, I have 1, 2, I have 4, 4, and I have 9, 6. And again, you can see I have a curve. Now the difference between the square root of x, which was the parent function, and 2 times the square root of x is I'm fatter from the from x-axis up. It's fatter, right? So I've been stretched vertically. So the domain, well, I can't plug in any negative x's, can I? So my domain is x is greater than or equal to 0. And my range is still the same. I only have positive numbers, so x is greater than or equal to 0. So we have reflections and translations of radical functions, okay? if we draw the graph of y equals a times the square root of x, all right, that graph starts at the origin and passes through 1a, right? Because our first x would be 1, and then we'd multiply 1 times a and we'd get a. Wow, I did not type well. This is the word graph. Okay, the graph is going to be in quadrant 1, right? I don't know if you guys remember, this is quadrant 1, 2, 3, and 4. So it goes counterclockwise, 1, 2, 3, 4. And just the basic shape of a square root graph is like this through quadrant 1, right? If a is less than 0, okay, so a is negative, that causes this whole thing to be negative, and it's going to flip our graph over, and we'd graph like this. It would be a reflection across the x-axis. So this is negative a, and this is a. Here we have a c on the outside. Okay, this is not part of the radicand. It's on the outside. If you have a c here on the outside, that moves you c units up or c units down. So if we take our base graph, which is just this red line right here, let's say. So, I forgot to say okay. Oops. So this would be plus c, and down here would be minus c. Right, it just moves the same curve up or down. And then if you have h is inside the square root, or it's part of the radicand, it's under the square root. That moves left if h is positive and right if h is negative. So it's kind of opposite of what you would think. So again, if here's our base graph, this would be kind of a minus h or negative h, and this over here would be a positive h.
So left is negative h and right?
No, right is negative, left is positive. So this is, left is positive, so this is positive and this is negative. So it's backwards. Like with the c on the outside, it makes sense. If it's positive, you go up. If it's negative, you go down. If it's inside, it's the opposite. If it's positive, you go left. If it's negative, you go right. Okay. So here's a reflection of the square root function. Our original square root function, you know, comes up this way, right? Well, to do our reflection, what we do is make a table. If x is 1, y is negative 3. If x is 4, y is negative 6. If x is 9, y is negative 9. So I do 1, 2, 3. Hold on, I'm trying to draw my curve. Okay. So again, our base function comes up, you know, here. So we've got not only a dilation or a stretch, we've also got a reflection. So it's across the x-axis into quadrant 4. Why don't you guys try this one? Now we have the translation. Okay, here I have this plus 1 on the outside. This is that C, because it's on the outside of the radical. Alright, so I'm going to again do the parent function. So here's the parent function in red. Okay, so this is just square root of x. If I do 0, I get the square root of 0, which is 0, plus 1, so I get 1. Square root of 1 is 1 plus 1, so that's 2. Square root of 4 is 2 plus 1, which is 3. Square root of 9 is 3 plus 1, which is 4. I am moving each of these points up 1. So I only moved up just one space. So if you know your points on your base, your parent function, so you know it's going to be 0, 0, 1, 1, 4, 2, 9, 3, then you just add to the y, essentially. Does that make sense? It's the y that changed. Now here I have that -2 that's inside, so this is the h. So it's negative, so I'm going to move 2 spaces to the right. Okay, so again my parent function would be here. But I have that -h, so I'm moving 2 spaces to the right, so I take every one of these and move it over 2. So from here I go 1, 2, from here I go 1, 2, from here I go 1, 2. Or if you want, you can plot points. But if I put a 0 right here, I'm going to get a -2 under the radical. Does that make sense? So if I say x is 0, and I can't take that. That's why there's no point here for 0. So now what I need to do is I need to think of, to make this a perfect square, what do I need to put for x when I subtract 2 from it that I'll get a perfect square? So if I plug in 2 for x, that gives me the square root of 0. If I plug in 3 for x, that gives me the square root of 1. I plug in 6 for x. So that gives me the square root of 4. And then 11 to get the square root of 9. Okay, so at this point, when you have something happening to the x underneath the radical, you need to do a little bit of planning to make sure that that gives you a perfect square. Nobody wants to plot decimals and all that annoyance, right? All right. Now we have multiple transformations going on. I have this negative outside, which is going to flip it over, and then I'm moving it one space up, and I'm dilating it. And apparently I'm forgetting to put graph paper on. Does yours have graph on it? Oh, okay. We'll just draw one. Okay. Okay, again, remember our parent function. Looks like this. That's our parent function, the square root of x. So I only have x underneath the radical, so I can plug in perfect squares for x. So if I plug in 0, I get this, so I get negative 2 times 0 plus 1. So that's just 1. If I plug in 1, I get negative 2 times 1 plus 1, which is negative 1. If I plug in 4, I get negative 2 times 2 plus 1, that's negative 3. And if I plug in 9, I get negative 2 times 3 plus 1, so that's negative 5. So I have 0, 1, 1, negative 1, 4, negative 3, and 9, negative 5. So we flipped across the x-axis, we stretched, and we moved up 1.